Yeah. So that's forwards and backwards. Oh, I probably don't need a microphone. Yes. Yeah, this is a microphone. Would you like to stand here or? Well, I'll probably go. I imagine I'll be able to speak clearly enough because everyone's very close. I shouldn't really need a microphone. Yeah, I just need the camera. Yeah, okay. You know, I mean, well, we're all sitting over this side. You're getting the food on the application. Everyone's like, if we have given you every day the same food, yeah, I mean, try to understand the real or whatever. Anyway, don't say anything.
But they may be food tomorrow because the droppers. Right?
Yeah, well, the droppers that will also be problem. Anyway, so
And one.
there will also be wine tomorrow. Exactly. Okay, but we can discuss this later. So we're going to now listen to my colleague's presentation. Thank you for being here and talking about the diagnostic use of the semi-geostrophic model. Please. I'd like to start by just saying thank you to Jochen and the other organisers for the invitation. Also, thank them again for organising such a nice programme. And I'm looking forward to the second workshop tomorrow. I retired from the Met Office just over a year ago, but this is basically Met Office work, which is why it's still on the Met Office brand. My previous talk, if you came to that, was new work, which wasn't on the Met Office brand, but I shall try not to say anything I shouldn't say. I think I'm still working with someone at the Met Office to cover this. That's wrong. Right, now this workshop's about connecting real geophysical fluid diameters using practical operational weather forecast and climate models, which use production and climate prediction in particular, well, climate prediction and weather forecasting, and with diameter understanding, such as done a lot trying to understand how things work in the atmosphere and ocean, though I'm particularly atmosphere in this talk, and also back to rigorous mathematics, which is good before, like that very nice talk we just heard. So this talk is very much just showing how all these things link together. The nature of the talk means that it's probably best if you ask questions during the talk, because the subject matter will vary quite a bit through the talk, so it may be best if you want to ask a question, if you ask it straight away, as the previous speaker also did. Now, first thing is to establish the rules of the game. So, in practice, if we're trying to forecast the weather or predict the climate, we need to use a model which doesn't have, let's say, a priori limitations on whether it's applicable or not. And that means now we've got big enough completely. So the Met Office now self-compressible navigations. Not everybody's quite gone that far, but the Met Office certainly has. And then you represent all the physical matters, couple the model to the ocean model and the sea ice model and the vegetation model and all these things, which matter a lot, thinking trying to predict the climate. The immediate effect of that is you don't get an answer, you don't understand it. No, those equations describe all classical fluid mechanics, so you have no idea why anything behaves as it does, you just have the answer right. Weather forecasting, we can usually predict weather about a week ahead on various case. In climate, we hope we can predict the climate, but this need to understand is really important in climate prediction. You really want as much evidence as you can, your climate model is going to give you the right answer. At the moment, the right answer is occurring all around us. We manage to predict it. It's a really dangerous situation. You don't really know what we're doing, and it's so important. So understanding for the production models requires the use of simpler models. Now, the point of the simpler model is, by definition, because it's simple, it has limited applicability. So you would never use a simple model for production because it would not work properly all the time. So the simple model has a role of telling you how the full model will behave under particular conditions. And since we're interested in a lot of particular conditions, that means you can't do it. The idea of universal simple model, people used to talk about quite a lot 20 years ago, that's maybe a bit longer than that. It just doesn't make any sense at all. You different simple models for different circumstances, and you probably need to be different according to which part of the physical system you're looking at. So just forget all about universal simple models. You want a simple model which is let's say there. Right. So they need to approximate the governing equations of the relevant asymptotic limits. And this is where the more formal mathematics are coming in. And there's lots of choices. There's no such thing as a correct asymptotic limit. There's an asymptotic limit that's relevant to the aspect of the system you're working with. And then they need to be mathematically well posed, because then, in principle, you can prove that they actually do approximate the performance of the full model when that limit applies. So, like, express that limit as some epsilon, which is something small, which you define what that means. And that epsilon tends to 0, the solution of the simple model should behave the same way as the solution of the complete model, and then you really have learned something. So the mathematics is very important. So you have to prove things are well posed.
Yes.
Okay, point for understanding. And unfortunately, there's a lot of simple models around that. Oops, a lot of simple models around which are definitely not well posed. I'm not going to go through a list of them. That was such a destructive talk. Well, there's a lot. There might be one or two of them. And ideally, you then make. Oh,
So this is, I think, Jerome.
yeah. Okay. Ideally, you should actually prove this back to a mathematical journal, and that really tells you something about why they're on average states in a rigorous way. Which you'd really love to have. Lots of mathematicians would like to do that, as you might expect. This has only been carried right through in a few cases. Some got fairly close to 3 more cases. So this is the thinking. So no simple model is universal. You need to choose one according to what you're looking at. Right. Okay. So my particular interest. One more here. One of the main applications of this is to understand systematic errors, and then obviously use simple models to understand that, and then try and work out how to fix the error. You'll see an example of that in the talk. That means a systematic error will essentially means you're looking at large space time scales, because errors on smaller scales, that's inevitable, and they not usually systematic. You still need to understand them and put them right, but that's it's natural to look at large scales, and I'm going to talk about large scales. That's what I works in myself, but remember, it's not the only thing you can do. Now, I'm going to start off by illustrating the principle of the shallow water model. Now, one of the key things about this is that part of what I'm going to tell you is that you shouldn't be using a shallow water model to explain large scale behavior, even though everybody does. Just be have in the back of your mind, I'm going to show you shouldn't be using it. But it's very useful for understanding, because I get give an example of how a lot of the principles work. So the first thing, a lot of people think the Rossby number, again, dimension parameter matters. That's the ratio of the flow frequency to the inertial frequency, but it's also another parameter called the Froude number, which is the ratio of the flow speed to gravity wave speed. Now, I have seen written down rather a lot that gravity waves are fast and therefore the Rossby number is small, and that is just completely wrong statement. So you have to be really careful about that. With 2 completely different dimensional parameters, they both matter a lot, and that will go through to make it. So this is completely different physics to this one. In fact, in the atmosphere, the rotation rate is not particularly fast. It's not anything like rapidly rotating fluid you might have in a laboratory. And gravity waves are sometimes fast and sometimes very slow. So these are both pretty non-trivial things. There's then a key scale, which is where the 2 are equal, which is called the radius of deformation. And if you try and match shallow water theory with observed behavior in the troposphere, like weather patterns, people have found that observationally, the shallow water model best matches the observed behavior. As you take the radius of deformation be about Calvin Killing. Again, you'll see that illustration later on. That's in the, I'll show that again later on, but that's the storm number we're talking about. And it's very important as to whether the Rossby number is smaller than the Froude number or the other way around. And when they're equal, it's another equal. So you see, things are a little bit less trivial than you might think. Unless you're used to this already. So now for the case I'm interested in, I'm going to concentrate on the low Rossby number for me. So I'll also cover the case for the Rossby Froude are equal. So I'm going to start off by saying starting with the Rossby number, the Rossby scale divided by the Coriolis parameter. Let's scale the standard definition used for this. And then I'll write down non-linear shallow water equations of dimensional variables. Everything seems to be order one, except with epsilon here explicitly, so there's dimensionless. And the fact that Rossby number is small said that these terms are small compared with that, so the epsilon to -1 there. And that means you then get something of any practical interest if this combination has is order epsilon, so that you can't only have one large term in the equation. And then when this equation will give you anything useful, which is order one, it's got to be brought back to order one, so these two have to cancel for epsilon. Same applies there. And the moment I've only said the Rossby number is small, I haven't said anything about these terms at all. So for the time being, I won't say anything about the equation at all. Everything's order one. That is immediately a non-trivial statement. If you're used to this, you might think that might have always there might be order one. Get that. Right, so the order large terms are just geostrophic balance, so U is geostrophic plus silence of U prime, and then to the next order, just say that's -1. Now you put in UG instead of U, this term is that's only an error of order epsilon, and that's the same other momentum equation. Here again, you haven't received anything small, so these things are there. Now you'll see immediately how based on particular choices. I'm going backwards. Sorry, I keep hitting the wrong button. Right. There are things you could do here. I could put UG there as well, but I'm chosen not to. And the reason is I prove that this is a well-posed system of equations that conserves energy, because I haven't approximated this U by UG. So I need to be consistent about my transport velocity, and essentially that allows you to prove energy conservation. But if you didn't worry about the mathematics, you could say this should be UG as well. And then you find you couldn't solve the system. So the mathematics does matter. Right, now. So that's what's called
arbitrarily choose.
Sorry?
You arbitrarily choose which terms you keep those terms.
I'm not quite arbitrary, because if I don't have the if I try to prove energy conservation and I put UG there, but I've still got a U there, I wouldn't be able to conserve energy. So when I try to use the energy equation, I'd have an inconsistency energy equation.
You just try to write down a system with all sorts of.
Yeah, so I want to. I know I must write down a well-posed system. So first thing, you make sure you have an energy conservation law, and you need a lot more than that. But that's a good place to start. Otherwise, you get something that's probably just straight away.
But obviously, there are many ways to conserve energy.
Yeah, that's right. So I'm showing a particular way where you can conserve energy, but it's not the only way. You know.
What will happen if I put UG in? I mean, instead of U, I put UG in this transport term, then.
Well, I have to put it in the third equation as well. I don't want to approximate the third equation and go into the same spot.
Okay.
Right. So, but you're quite correct saying that there are choices, definitely. Only some of them will give you energy conservation, mass conservation. I want something well posed, and I have a much better chance of proving that if I've got energy conservation and mass conservation. So this model was invented years and years ago. It's called the type 2 geostrophy of the history of meteorology. It's a classic model that was invented in the 1940s, like quasi-geostrophic theory, also invented now. People around then didn't have big computers, so they spend their time understanding the theory properly. And this is an outcome. This is one of the outcomes. And I'll delete it essentially.
Mike, can I just quickly, I see you haven't split up H into a geostrophic and an ageostrophic.
Not so far, no. At this scale, I don't want to. But other scales, you might. I'm going to mention that. But yes, that's very significant. I haven't changed that way. So, so this called setting from does conserve energy. Now, the important thing I've got to do is to make sure that this term and this term are the same size as this one. You do have to do something very non-trivial to make sure that works. And the Froude number is the gravity wave speed depends on h, the h in dimensional terms. So by saying that this term has to be the same size as this one, I'm implying something about the Froude number straight away. So, and if you work through it, I'm not going to go through the algorithm that shows it now. It was, I think I did do that in my first book. Actually, the Froude number is accepted sine to a half. And since there is a deformation, it's defined where Froude number is order epsilon, so it's equal to the Rossby number. That means it means you look at the length scale larger than the rate of deformation. Now, I'll probably mention the other case at this point. Now, in order to get the Froude number equal to 1, I need to say that this term is bigger than, there's a mean value of h, which is larger than its variation. And that's what leads to quasi-geostrophic theory. So now put scaling into this equation as well to get quasi-geostrophic theory. And that's a different scaling. And that would lead you to Froude equal Rossby, which is quasi-geostrophic theory. And that also conserves energy and mathematically nice, but it's not the one I'm looking at today. So there's two different ways of getting some geostrophic to leading order, and they were called very boringly in the 1960s type 1 and type 2 geostrophy. And the quasi-geostrophic theory due to Charlie. And they did talk to each other, they actually worked together quite a lot. Right, now one feature of this, which was in the previous talk, is that by doing things this way, the kinetic energy is order epsilon, while the available potential energy is order 1. And quasi-geostrophic theory, they're both order epsilon. And you immediately think, well, parakinetic conversion is going to convert between available potential energy and kinetic energy. And this says that you can never really tap into all the available potential energy. And what's happening is that there's a huge amount of available potential energy in the real situation in the pole temperature difference, but you can't tap all of it into the storm, which is probably just as well considering how much there is. So to put them on equal basis isn't really correct on large scales. When you get down to a smaller scale, look at, say, patches middle latitudes where storms develop, you can say, well, essentially assume everything small first available from reference profile, and therefore you calculate available potential in respect to that, and that means you can then make them equal. So looking at smaller scale, quasi-geostrophic theory does, you get them both smaller epsilon. So it's very important to make that distinction. The next point is because actually the history, because semi-geostrophic theory was then explored from the Genesis, where while looking at a local patch with a very anisotropic scaling in the horizontal, that you need assume constant rotation, which is a patch or a front forming. But if you look at the large scale, you absolutely have to have the correct Coriolis parameter, and that can be used. And or at the end, the conservation still works. And I seem to mention, I showed you what's effectively the second order model in this limit. The first order, leading order model is planetary geostrophic model, which oceanographers have used a lot historically to understand ocean basins. But really, this is a second order extension to planetary geostrophic, and obviously variable rotation, particularly fundamental in that model. So that then gives a chance to mathematicians. So constant rotation includes long time difficult weak solutions. Probably need variable rotations in the atmosphere, and prove rigorously that short time variable rotation, and the formal argument suggests long time variable rotation. But those are what's happening there, the mathematical structure that you're able to make some very clever tricks with constant rotation, which of course don't work with variable rotation. You can generalize the argument which forces the mathematicians to have new concepts of what you mean by a solution and new concepts of what you mean by a well-posed optimal transport problem. Mathematicians don't like new concepts which come from physics. Charlie knows all about this. It's a case of plain mathematics. No, you need to have a slightly more general form. So this is why this interchange across the board is really important. So this is still not solved rigorously. by best explain people to do it. And the other thing is mentioned, we obviously express the slow evolution of shallow water by potential autistic infection, potential auticity, relative auticity plus the Coriolis parameter divided by the depth. On scales larger than the range of deformation, Coriolis terms swamps of auticity. So really, everything dominated by variations in age. If you look at a geostrophic system, that auticity term isn't there at all. And that means that you need, when working in this limit, all you really need is a single evolution plane for age, that embodies potential auticity. Potential auticity, where this is a function of age. Right. So, now just to show what happens in this limit. Now, there's two published examples of showing how this limit works. Just emphasize the computations all with full shallow water, not with any simplified version of it. So this is a paper by a gentleman from Japan, and what they show here is they compare they take the same Rossby number for the same rotation rate in both plots. Here you've got a small crude number, which is something near the QG limit, particular latitude. And here you've got a larger crude number, which is more like Rossby number of half, actually the 7 geostrophic limit, which is away from the equator. And you see, you start with a random distribution of auticity. You see in this case, coherent structures large, near the equator where we spread out, both hemispheres. And here with a smaller crude number, everything gets spread out. So this is really genuine two-dimensional turbulence where in the long term, everything just goes to only symmetric flow, that's crude. While in the 7 geostrophic limit, you retain all your voltage you start with, essentially. It's a very different type of solution according to crude. And another example, this is done by PhD student Andrew Weed, who worked with Lex University a few years ago. Unfortunately, he never got the chance to publish his own results. I put them in my book. He doesn't know I've done that. Now, so this is a classic example of what this is. These are potential auticity plots after certain lengths of time. So the quasi-geostrophic limit, the rate of deformation is just 1 all the time. We're going to take Rossby equal through both tending to 0. You take the 7 geostrophic limit, effectively it says the rate of deformation tends to 0. So you get large because the ratio of Rossby and the crude number obviously tends becomes large once you go to small as you style tends to 0. So in this case, the rate of deformation gets smaller and smaller. And this plot is unstable, almost like the initial data, or the initial data was on the plot. On quasi-geostrophic, then with the rate of deformation independent side, and instability developing, and these solutions are quite different. This one in carbon is actually going pretty well nowhere, and this solution is developing due to nice instability. So
So can you explain a little bit what are you plotting here?
plotting potential water from full shallow water.
So this means that there is nothing, it has nothing to do with the model that we saw before.
The previous plot was again full shallow water on a sphere. This is full shallow water and more idea.
No, but
These are not the simplified models. These are full shallow water.
the equation, the system of equation that we saw that was beginning.
That was the very beginning. I showed you full shallow water and decided on it.
Okay.
So and that is the solution to that equation.
Which one?
The full shallow water with an inside on it.
Okay, and here?
Here, this is full shallow water inside and it in different ways of finding inside.
So what is the value of epsilon here?
So in this case, so with the epsilon where I wrote up for this solution, to get this, I have to put epsilon in the continuity equation as well.
The point here that the first one epsilon is group number and the second.
Yeah, I'll go back. Right, so I'm going back to here, right. Okay, so this is the I call 7 geostrophic limit. That's the lower plot I just showed you, and The other one is quasi-geostropic limit, where this term, that's electrons and -1 in front of H, which means the horizontal divergence has to be order epsilon to make this equation work.
So can I ask another question?
Yes.
Sorry. So, U here is the velocity.
Yes,
So, but your plot is the velocity.
the potential vorticity.
Sorry?
It's the potential vorticity, not just vorticity.
Okay, what is potential?
The disease plus, I've shown you the formula before.
Ah,
That's it. Thanks.
The theta plus f.
That's just what I plotted that.
but so what is the relationship with the, so the, okay, the zeta would be the rod of U
That's relatively, yes.
As
plus F. So F is.
Coriolis parameter.
Background rotation. So this is the total rotation of the Earth.
And then you divide by H.
That's
It's a conserved, materially conserved quantity. Which is.
So this is what you are, this is the potential vorticity, and this is what you are plotting
that's
in
what I'm
the.
talking about.
this is called Earth's potential,
Yeah.
But for epsilon,
which is not the same thing.
I define that in different ways. I put, I'm showing really different scales.
yeah, okay.
So the bottom block is the, well, sorry.
For a plot potential for the.
You were trying to operate.
I'm trying to work out what I didn't show. Must be hard.
So and D,
Right, so this is epsilon as I defined on that slide. So I call it semi-geostropic scaling. And this is a slightly different way of inserting epsilon into the equation, which I just described. But epsilon also appears in the equation for H.
but what I am saying is that for the epsilon here, you don't say what's the value exactly of the epsilon, because you have to,
This is just a particular small number.
you don't, okay.
Well, obviously I know what the answer is for all sorts of different ones, but I'm just can't put more in this talk, so I'm just showing some examples. Same value epsilon, defined differently, same time, and key difference, the answer is very different. This answer is very close to initial data, which again, I haven't shown you, but what's happening, it's almost the same initial data. This answer is definitely not the same, we've got the same data, and I think this instability is growing a lot.
But sorry, another question, because this is a plot. So the way you do it is that you come from the equation, you compute U,
Yeah,
right?
right,
Any
okay.
value, and then you from the U you compute the vorticity.
Yes.
That's how you do it numerically.
Yeah, that's right. It's all numerical solutions. So I just use the same numerics I've done with solve the equation in the first place. Solve the equations and diagnose the vorticity and calculate the potential vorticity.
Okay. Thank you.
Right, now, right, now, I need to explain this bit. Now, if I consider constant rotation, and I simply substitute, if I substitute, right, if I now say, right, I'm now going to create an equation for H after the order one equations, so I just substitute, obviously UG and VG are just gradients of H and then equations at the top. I then find a massive calculation of terms, which I'll try to figure the sort of introductory lecture if I go through that and walk. Time for that. And what we find is every calculus order epsilon by gave you the order one. This is called geostropic degeneracy. And when people first did this, they said, well, there's nothing to evolve at all, and it's very boring, so we need to do something else. But what it actually tells you is that even if the time scale is slower in order one, it's order epsilons and minuses. And one of the things we're trying to explain is why the atmosphere gets stuck in the same pattern for ages, and then something happens and it changes. But it's characteristic of the atmosphere that the weather pattern gets stuck for long periods in the same part of weather, and that's why you get anomalous weather and serious impacts. And the natural dynamics of the system is that your two-dimensional model is you get stuck all the time. And if you now allow for variable rotation, then calculations doesn't quite work. But the terms you get left with, or the length scale divided by the radius of the Earth, is typically quite small. And so you still get a very slow evolution time scale.
Sorry, I have a question. So with variable rotation, you mean that the Coriolis parameter varies?
Function of the, yeah. So this cancellation of all the linear terms only work for constant rotation, but the derivatives involving rotation are still pretty small because it's considering a scale parallel to the radius of the Earth.
So you throw away lost count. So you throw away lost count.
well, if you have constant rotation, if you've got, well, yeah, but I mean, rocky wave terms are going to be there in practice, but they're not very big. You have to have them. So the first bit, so it means your evolution time scale is smaller than you might think, both because you have higher order terms.
You can do this here on the rabbit slope.
Yeah. So the two examples I've shown you would be both cases where, except the equator, the range of deformation is always very large, the rotation rate correlates tends to 0, and you've seen the both examples of everything got stuck. And that's and that was realised years and years ago, but in fact, people sort of thought, oh, I don't want something that does something, so they tried to think of something else. What actually happens in the atmosphere is all the time it doesn't do anything. You actually need to realise that the natural dynamics of the system is to get stuck. It still includes three-dimensional effects. And so if you're looking at variability and trying to sort of then get a low-order system to explain long-term variability, you need to realise that this is what behaviour is. So to summarise that, so the Rossby wave will effectively effective variable rotation, which is our Rossby wave, is giving you about 15 meters per second west propagation, or non-dispersive. It's independent horizontal scale, unlike the stick case, and that's essentially why you get long enormous tropospheric circulation. The development of decay requires paraclitic dynamics, three dimensions, and that will then give you the observed transient behavior. So transient behavior will be dominated by three-dimensional effects. And that means it's really dangerous to use a two-dimensional model in trying to do very idealized studies of atmospheric variability away from the equator, because there wouldn't be any if you used a valid two-dimensional model, and you need to represent the effect of three-dimensional effects.
So excuse me, so
Yes.
when you do that numerical simulation, again, sorry, to come back to that, do you have like, so do you live in a, which domain are you living?
Okay, there's two different ones, but that's we were interested on a sphere with the correct Coriolis parameter.
Do you do it like,
Yeah, and the salt channel, that's why it behaves. You hear it behaves the same way near the equator in both simulations, because the rotation isn't dominant anymore. There's away from the equator, they behave quite differently. Near the equator, they're not very different.
equator? It means that you have like a boundary?
No, there's no boundaries, just the rotation goes, the effective rotation rate to shallow water goes to 0. Because the the axis of Earth rotation becomes horizontal rather than vertical. Coriolis parameter is the vertical bit of the Earth's rotation vector, and that vanishes at the place. The behavior is totally different than the equator.
There's no Coriolis balls at the equator.
No, not in a shallow water.
It's not in this one.
And this integration was done on a middle latitude plane. I don't know exactly how big it was, but it's not a global integration.
But effectively, like east-west is periodic, you know?
I can't remember exactly what it's probably, but I can't remember the details, but it's probably constant. It's probably a piece of plane latitude spreading.
But your point is kind of that, at least that in the bottom one, these structures just propagate.
Yeah, that's right. There's a good drifting west with right. And essentially, this is more or less the initial data. Yes, nothing's happening, it's drifting westwards here, it's plenty.
Right.
Sorry, since you stopped, the regimes in the atmosphere you talk about are blocking or are blocking a type of sort of regimes, or is it just?
Well, I'm saying that blocking is essentially the word that's used to describe large scale anomalies, and this sense blocking is normal.
Okay.
I know you don't really have to try, you don't really have to do research to explain it, use the right limit, which happens all the time. And that you actually look at what happens, it happens all the time.
Thank you.
Okay, bit like no, all the time. Right, now the other thing about paraphysics dynamics is that the whole point of having these absolute eddies is to transfer heat from the equator to the pole, which is the point of applying it. It's how the circulation works. So you have a direct heavy circulation properties, so the sort of subtropical jet, about 30 degrees away from the equator. And then because rotation becomes important, you can't, that sort of circulation can't operate. You have this what's called paraphysic energy transfer. The key thing is that these eddies have to be able to transfer heat. Now, if you have a two-dimensional model, which is essentially geostrophic, then you don't transfer any heat whatsoever, because everything's the same at all heights, and the essentially there's no geostrophic temperature convection at all. They can only transfer heat very inefficiently. So it's fundamentally necessary to have paraphysics. So this is reanalysis data emphasizes that. So the solid line of the heat transport function scale is averaged over 30 to 50 north in the troposphere, and you see the heat transport peaks the deformation ranges, which wanders around a little bit with season, but it stays large all the way up to the larger scale. So everything is paraphysic on the scale of larger rates of deformation, and that's not always realised. And this plot, that shape of that curve is almost the same as the linear instability curve of the ED problem. It's an idealized linear problem of paraphysic instability, which shows that the effects of paraphysic growth only decay very slowly as you go to larger scales. It cuts off very sharply at small scales, which is why that nosedives. The energy spectrum is shown here. You see above the range of deformation, it actually flattens out a little bit above the range of deformation. You see that defined by that peak, and then it sort of becomes sort of slightly increasing, but wandering around this total energy, by the way, not kinetic energy, total available potential plus kinetic energy level.
So sorry, the range of information around 1,000 or?
Well, this suggests it's a bit smaller than that. Now remember, this 1,000 kilometers is based on a two-dimensional model of the behavior of the real system. And I've said the two-dimensional model is fundamentally defective, it doesn't have any paraphysic growth in it. So that would give you make a little bit nervous about estimating the range of deformation that way. If you estimate the rate of deformation by where the process converting potential energy to kinetic energy is the most efficient, we look for the peak in this peak transport curve, which is there. And I think it would realistically take that as a rate of speculation.
And this would be, so wave number 10 would be like 40,000 kilometers divided by 10. So what I'm convert this to length scale.
No, that would give you that gives you the wavelength, then it's converted to length scale divided by 2 pi.
Oh, okay.
Which is quite big. So,
It's a proportion as a fraction of the radius of the Earth.
the way the horizontal scale is done by the wave number, which is what the factor is in the wave, and how big the grooves are. And the wave number is 2 pi times less than the wavelength.
And this is just a number. It's not actually one. So,
This is an
no, one is right. One is what?
Yeah, what is one? Well, one will be wave number one, which means that 4 times divided by 2 pi.
Yeah, that's what I mean.
Yeah.
Right.
Have a 2 pi, which is
Yeah, I did forget about the 2 pi.
that's quite, in fact, almost 10.
Yeah, it's a lot. I understand this.
Someone else out a bit. Right, so scale larger than the deformation radius. the edge spectrum is fairly flat, but then becomes, well, on those plots, it's more like -2.5 than -3, but it's sort of fairly close to -3. Other people claim, which is not worry about that. So that transition, the wavelength is about 5,000 kilometers, divided by 2 pi will be more like 800 kilometers per hour. I wouldn't get too worried about that difference, remembering that if this is a shallow water model, which doesn't have any idea of baroclimate effects in it, so something that definitely does have oxidation effects in it. So I wouldn't get too. So, and then the small scale below 500 kilometer wavelength, which is essentially, so I haven't shown small scales here, but the aircraft data people look at a lot. This -5.3 slopes eases out to about -5/3 smaller scale. And that's so if you look at the aircraft data, we look at a lot of spectrum as shallows, but between 500 kilometers and 5,000 kilometers in terms of the wavelength, you get some very steep energy spectrum, and that means that there's a rather weak coupling between weather system, which scale larger than deformation maybe, the small scale turbulence. That's the only reason the weather forecast.
Excuse me,
Yes.
can you say something about how the spectra are derived? You take a snapshot in time, the average in time?
Right, these are real data, so that average in time over a lot of cases for that particular season.
So you take also,
So these average in time over the calculated 3 separate vertical levels and the latitude band from reanalysis data, but obviously grid point data at some fairly high resolution. And then you average in time over the season, you average over 3 different vertical levels, and you average in the we don't really have
so this is not that you are saying identifying some kind of crazy stationary situation or something like this.
Yeah, I'm not looking at instantaneous data, but I'm looking at time average.
Okay.
Right, so I've said all that. So the key message here is that the simple model of the extratropical large scale flow leads to 3 dimensions. That's where all the transients is coming from. And it's never negligible. Look at what's happening, it's always there. So so to try and construct a low order model of large scale variability, you need to start off with a 3-dimensional model that we just thought Stefan was talking about the week before last. And a 3-dimensional model, and then you will find a low order version of that. Right. What time have we got to stop with this? But there's more to show, right? What's our deadline?
Oh, sorry, I'm sorry. It's fine.
When you
Very
start,
certainly, I mean, now, how much?
45 minutes, I forgot to start it.
No, we've had almost 45 minutes. I've only got to about a third before. Because we've been having a very good discussion.
So, I mean, okay, so we have basically between now and the launch is half an hour.
Okay, well, I'll make sure to get through it within half an hour, including discussion.
Yeah.
And then we're going to have a separate. It's better like
They might start to rattle with this
No,
in kind of.
it's better to have discussions like this when I show things, especially with these discussions. So I'd rather keep going like this. Right, okay. Right, now, I'm now going to switch 3-dimensional models and end up with diagnostic into the 3-dimensional simple model. So I've said that, so I'm going to concentrate on the semi-geostropic model. So I'll mention how related to the quasi-geostropic model is different. So if an active approximation of the next scale breaking range of deformation. So in 3 dimensions, this turns into a condition of the aspect ratio has to be less than f over n, where f is the Coriolis parameter, n is the Brodmann frequency. And that means that it can be accurate for shallow disturbances, even quite near the equator. John Messon is not come to know this big explosion. Now the other thing about everything to be reached from the pressure, and really for using this model when you're studying real data, you don't have to make any approximations other than geostropic and hydrostatic. So write down the fully claimed unified model, identify how the model sees the geostrophic hydrostatic balance by the equation, make those approximations, and derive an evolution equation for pressure from those equations. I'm not going to show that slightly abbreviated because I don't enable those to got algebra. But the quasi-geostrophic theory, which is valid for scale comparable to range deformation, so aspect ratio H over L equals F over N or comparable to F over N. Now, more complicated pressure and the vorticity contribute equally to the potential vorticity, and therefore you can't apply everything in terms of pressure field. And the other thing is to make that work, you have to make additional approximations which you don't want to make on real large scales of real case, but you can make them in idealized cases where the quasi-geostrophic model is very useful. So, for instance, you don't have to use a reference value of the Coriolis parameter and just look at the beta term with perturbation to it, and you don't have to assume a reference value of static stability and say, look, it's small perturbation. Now, both those approximations are horrible with real data, but very useful with idealized data when you both for understanding and validating numerical methods like that. But if you're doing real data, you can't do that. So that's why can't use semi-geostrophic model prognostically, because it's only valid on this scale, but small scale behavior is horrible. So don't bother. And if you try to integrate prognostically, you start finding that out very quickly. So it's very useful diagnostically to take real data and simply work out, as I'm going to show in a bit, how the large scale behavior is determined. Right now, what I actually have to do to make sure I get something useful is use the full equation for the unified model, which are terrain following coordinates plus spatial geometry, fully compressible, non-hydrostatic equations. So I'm not going to write all that down because I'm still the screen algebra. Not very helpful. So this is a slightly simplified version. This is not the one that I've done computation. Besides that, so I'm just going to write down. We're going to make it hydrostatic. I'm going to use plane geometry, not considering mountain, all over the course of the real calculation. S is a generalized diabatic heat source. So that leads into these two horizontal momentum equations. So this is the pressure gradient term in horizontal, hydrostatic balance in vertical. Potential temperature is some source term S, continuity equation, and equation of state. Keeping the fully compressible formulation, that's going to show you can do that. It's very important to keep that consistent with the unified model if you're doing diagnostic. Now, to get to scaling, the key thing is the big issue with doing the scale analysis of 3D equation. These two terms are both huge. If you simply put them at face value, you think hydrostatic approximation is incredibly accurate, and you wouldn't bother with a non-hydrostatic model. But in fact, they're not nearly as huge. But what you can do is subtract a reference station hydrostatic balance with a constant theta and get the real non-hydrostatic dynamics. So by doing that, you can change this equation to look like this. But the temperature doesn't change, it's subtracted a constant. So these terms are now much smaller. Theta prime and theta rad are still not small, that small, a lot smaller than they were. And that gives you a much more realistic scaling. And it's very important to do that. Well, totally wrong impression of how big the fluid number is in particular. To get the quasi-geostrophic model, what you do is sorry, it's that. The quasi-geostrophic model, theta ref is now a function of height. And that means you're assuming that the reference state is a function of height, which is not really true if you look on very large scale. For regional use, it's very useful. That gives you a different model where you now acquire an extra term in this equation, which is the vertical vector reference state. But here, it's factor of constants, and this equation doesn't change at all. And I get this, at least I managed to get the term transfer this. And now work out through number from them. So I'm again considering the rotation dominated limit. So final is the Rossby number. Now I'm going to use variable rotation. So I'm going to say the Coriolis parameter is F0, effectively twice the Earth's rotation rate, and mu is a dimensionless function of position, sign of latitude. So I'm assuming that limit, remember, it's going to degenerate very badly in the equation like that at the moment. And that's got to equal the square of the Froude number, that's the Froude number. So the velocity divided by the Brazil frequency divided by the vertical scale. And that then leaves with these equations, what we'll do it, how you get there is you're going to say the vertical velocity is the horizontal velocity times the aspect ratio, and you're going to say the vertical pressure gradient is the inverse of the aspect ratio times the horizontal gradient. And I'll note that this is such a change of the quasi-geostrophic theory. You can say this term is actually going to be much bigger than this in quasi-geostrophic theory. So this is again where the two theories depart and the value in different positions. That then leads you to these equations. And you've noticed that this equation is what it was before, this equation is what it was before. This equation hasn't changed from where we left it off the reference state. But this now has its silent in front of it there. So it's a bit analogous to the shallow water motion. I'm just having it silent in front of the acceleration terms. So follow what we do with shallow water. So this is now the Coriolis parameters got to be represented by mu from Appleberg rotation. That's the geostrophic wind, no geostrophic vertical velocity. So I'm going to say mu and UG plus water epsilon, remembering that this is a somewhat dangerous issue near the equator. Your Rossby number is not universally small. And then this is semi-geostrophic limit, where we put epsilon in front of this term to have the geostrophic momentum, and then the same thing in the shallow water equation, and just formally the difference in this is 4 epsilon squared, nothing else changes. And so qualitatively, it's just doing the same thing as in the shallow water case, and noting there's a significant difference between this quasi-geostrophic theory. And now we can just, I need to show you the structure of this equation. So now I've just reduced everything from equal into the equation to the time derivative of pressure. That's pressure, that's actually pressure, so functional pressure. And without worrying about the detail, the structure of the equation, the matrix time, this is the total trajectory, this is not the geostrophic wind, this is the total velocity. So time the matrix is equal to 40. So this is like the geostrophic advection, and these are the effects of the diabatic forcing. So if you manipulate this using the continuity equation, you actually get rid of this term, and you find the evolution is controlled by the geostrophic advection plus the diabatic forcing. And then you can then leave some of this term out and say, well, I'm only going to see what the effect of diabatic forcing is, and leave this term out, or I can look at the effects of pure dynamics and leave this term out. And you can see you start using this diametrically. And this is the total trajectory, so you then back out what this is and say, well, how much is this affected by diabatic forcing as opposed to pure dynamics? So you can see because of this simple structure of the solution, you can it becomes a very powerful diagnostic. And now when Paul was giving his talk a couple of days ago, I was thinking about using this to diagnose breakdown of balance and clear air turbulence, something to do with it this last. So Q, so effectively this is Coriolis term squared, both it's squared, so you cross the equator with it, okay. This is the static stability. So to get towards very balanced state, these terms, and the diagonal terms dominate the quasi-geostrophic theory. This will just be the reference static stability. This will be the reference Coriolis parameter square, and everything else will not be there. So you get a constant coefficient matrix, just diagonal. In this case, you get a variable state-dependent matrix. And when this theory starts to break down, what will happen is this, this will cease to be strongly diagonal. It's going to be dodgy near the equator, obviously that goes to 0. And if you stop being strongly diagonally dominant, it really tells you the both have strong sensitivity to forcing, and you start questioning whether the theory is valid or not.
But there are lots of new terms, right? So
Yes,
So if you go near the equator, then all the neutrals disappear.
yeah, so what happened, I'll tell you a bit more about the place in a moment. Right, on there, but yes. Well, that's going a bit further to that. So that allows you to complete solutions up to a single scalar variable. But this has to be positively definite to be the way to allow you to solve it at all. So the first thing the mathematician has to do is to show that if you chose initial data to be positively definite, you would always solve the system indefinitely. In principle, it's quite possible for that to break down, then you couldn't solve the system at all, and you couldn't get a long-time existence result, and you couldn't really say this is a proper limit to the order of claims you can use. So it's really important to be able to do that. And this is where optimal transport theory comes in, because optimal transport allows you to prove the existence of solution with properly definite. Built into the optimal transport method. If you do this with the quasi-geostrophic model, this is constant coefficient of the definite matrix, so that issue doesn't arrive at all. But QG is very simple mathematically in that respect. The other thing is have certain state dependent, which is really important. A lot of what really happens sensitivity to constant coefficient matrix, strong sensitivity to atmospheric structure. And I'm thinking what Paul was talking about, so you have an example of that. But you immediately see if you allow these coefficients to have small scale variations in them, you will be very suspicious that your large scale solution depending on small scale variations they can stay. That will really tells you it's not it's only going to work on large scales, and in particular, these coefficients must only represent large scale variations. So if I just show that again, if you calculate this from high resolution data, there's no way to probably better. Something seems to be huge. That just tells you the theory that's not valid on that scale. So you've got to be very careful with that. The diagnostic piece. All right. So you have no forcing then to determine that matrix is conserved constant rotation, only very slowly with variable rotation. The individual eigenvalues can vary a lot, determine just the product of them, and that gives you observed anisotropic behavior, which you really want to exploit in diagnostics. And talk about small eigenvalues being that's what you can really use the model from sensitivity to forcing. So the structure of that matrix is really important. And it tells you both how sensitive model is forcing, so weak stability will be large response to forcing and probably break down the model altogether if it's very weak. Right, so I've covered once again the other. I'll go most of look at sort of the last paragraph there, so I think I've said enough about that. Boundary layer friction can be incorporated because that's purely a function of pressure. The equity boundary layer is purely expressive, being a function of pressure. So I can put that in. Usually with real data, it's quite important to do that, especially with topics. I'm not going to go through details of that. It's done. It's done for results I've shown you. And anthropics is answers your question. Right now, you basically can't have a geotropic wind, you have a non-zero pressure gradient. The rotation rate tends to zero when it blow up. So what happens is the theory degenerates a weak temperature gradient approximation, which says you're not allowed to have a horizontal pressure or temperature gradient. That's a protection have to use zero. Not quite true if the rotation rate is small. And that is well known to be very accurate approximations of what happens in the tropics. Within 20 degrees of the equator, that is actually very accurate approximation for real data. But I don't think this is totally trivial, so why use this model? But what happens is forcing has large horizontal gradients, tropical convection, for instance, huge spatial variations in the tropics, putting land, sea, mountain, is just a natural variability of convection, right? And that means that you, involved in its ageotropic circulation, need to remove the horizontal temperature gradient that convection is trying to create. And that is actually a very good model. You can see an example for a leading order tropical circulation, especially having orbital circulation. So it's actually very useful in the tropics in terms of shouldn't be used. This principle of maintaining the temperature gradient is very robust. The more complete dynamics is actually quite zero. It's quite, you look at semi-shear antibodies analysis, tropical temperature above the boundary, and it's very small horizontal gradients. So we'll see that being exploited in a moment. Okay. So I've used the metal, well, these examples use metal is unified model on a 40 kilometre grid, but I first of all built up small scales to how I hope semi-geostrophic theory being valid, but certainly it was anything on a scale of 40 kilometres. So reconfigures the course of revolution, smudge things near the equator, run an F squared on the diagonal term of that matrix. So all I'm doing is smudge the equator itself, probably won't get the right answer, but get an answer. I calculate, now remember, the unified model doesn't know anything about the positive definite condition on the pressure. So it will have situations where that measure isn't positive definite, so I have to smudge things a bit. So it is, otherwise I can't solve it. When I do solve it, and I use physical forcing with what accumulates over an hour to get rid of time step noise, which in this first unified model of convection is horribly intermittent. To try to assume that we define a balanced response is totally wrong, that we get on something else. So essentially, I'm imposing something like the validity of the semi-geostrophic model on the unified model, which is obviously not the semi-geostrophic model, and some other things as well. But we'll do that, and then we'll see how well it works. Right, so first test is you calculate the geostrophic movement unified model pressure. So I'm just assuming that this example I've just shown you somewhere over the Atlantic, so safely at middle latitude, safely away from mountains, it should work there, works anywhere. So that's the geostrophic wind, which will store. Then I'll calculate the geostrophic wind from my semi-geostrophic solution procedure. I'm just going to remind you of that bit.
So this would be Q minus.
Yeah, I understand a bit of that, yeah. Right, okay, so this is the total velocity. I'm comparing the geostrophic plus geostrophic. So first of all, I use continuity, but I multiply by Q to the minus 1, and I get rid of this term of the continuity equation, get a sort of linear term in rate of change of pressure. I solve that single equation pressure, and now I know this term, and then I can back this out. So I go through all that. Right, so now we get to this. So this is the so the bottom panel. Remember, I haven't used the unified model wind at all in this. So the unified model pressure. So this is the unified model's own velocity subtracting the geostrophic wind I've calculated from the unified model pressure. That looks like this. And this is the geostrophic wind calculated from the diagnostic calculations. I've worked out the total velocity and subtracted the geostrophic wind from it. So these should be, well, the theory is really accurate. These two should be the same. As soon as a fair degree of resemblance, I'm quite pleased managed to get that close. So, quite strong correlation. One thing to do that is the diagnosed geostrophic wind is rather larger than the real one, especially here. And that's actually a common feature of semi-geostrophic. It tends to exaggerate geostrophic wind when it's not coming in. But that was good enough to match for me to be, well, given I'm just using real data with a very good modification, I'm quite pleased to get that close.
What is this Cullen scale then?
Color scale on the right.
It's meters per second.
Yeah. Okay.
Is there a reason the bottom you didn't get?
So that's the total of 60 meters per second. The edge is top half.
Yeah.
So what you're asking on that?
In the top one, there is a deep blue lobe at right in the middle, which is not in the bottom one. There would be no worse.
Well, this is the model minus geostrophic losses. So this is probably an exaggeration estimate of the geostrophic wind and semi-geostrophic model. You have a small eigenvalue in that matrix. When semi-geostrophic theory starts going wrong, the symptom is to get too much geostrophic wind. And that's why it's very dangerous. That's why you never want to use the prognostically, because you shouldn't tolerate that sort of behavior in prognostic model. It's a very good, when it starts going wrong, that's what it does. Essentially, there's no the total velocity is just a diagnostic, so it doesn't obey any energy conservation. You have as much as you like, just doing really silly values. So this is my immediate guess. This is a place where there's a weak or item value in that matrix. Now, this is not a very accurate estimate over the this is what you believe. This is the,
I know this is on much smaller scales. It's not,
it could be I haven't looked at the data about it consistently with the validity of the model, but I always do very crude reconfiguration. That's why I sort of quite really pleased to get that first, given I've started with a real data set, nothing special about it. Did a very crude type of filtering and then hope for the best, and it actually worked quite well. So we have about sensible expectations about this.
Yes, sorry, there's a question. Multiple QGs.
My problem with QG is I've got to get real data with QG framework. I've got to see a reference point on those parameters. I've got to see the space uniform reference state. It's probably not a good idea of that big region.
Just to work it.
Yeah, well, when you compare with QG, you need to move into a situation where the other assumptions are dominant of a smaller region. Stable coordinate time doesn't vary too much. Mean static stability doesn't vary too much. And then what happens is you look at the scales like QG itself. Then have leading order accuracy, we can improve QG second order accuracy, and then QG will then be much more. Thank you. So large of this, you don't have to make the extra population. And you don't have to do that iteration. QG used a lot of the basic first order form, it's very simple. To make it accurate, you need to do its outer iteration, cover a lot of accuracy in that minute. It's demonstrated very well 20 years ago. But sorry, they don't really have a simple model anymore. So I haven't really seen that formulation being used very much. There was invented and done really well. But that's the history of it. And this is what I've left out. And this is the difference between general and calculating the pressure of the model minus. That's the model U minus more than 30% of the geostrophic theory in the lower troposphere of the boundary layer. This is a 2-week average, so look at the longer time scale compared with averages of the upper troposphere. And you see that average over that time scale, there's hardly anything missed at all, except very close to the equator. So you miss a lot close to the equator. You don't have Kelvin wave, probably the biggest contribution to that. So looking at time, you can get pretty well everything. And of course, when you look at just granularity, we're really looking at the time scale. Should get that, just. Right. Now you can play now. Right, now you play. So you work, you incorporate the leading order effect of latent heating in sort of the Q matrix. You take if S is the latent heating, you take it across the other side of the equation and replace its dry static stability with the void static stability. And so algebraically comes to the same thing. And this is our vertical motion times dry static. Replace that with void static stability. The difference between those two calculations is that for latent heat release, how you define void static stability. And you can play that trick to see how well the latent heating coupled with the dynamics. I've got my example. Right, so these are the this is the vertical motion from the diagnostic. And this is the long vertical motion. Again, you can see a sort of reasonable correspondence. They're not quite the same, but again, the model is the same as being more unified model behave reasonably well like a balanced model on these scales. Or if you say it's not, this is a reasonably good approximation. Whichever way around you say it, but the two things match fairly well, certainly enough to be useful, not well enough to be prognostic, substitute for prognostic use, of course. Now, then that's a simulated heating, so Brighton. So this is the This is latent heating straight out of the model. So it's latent heating is unified model, time average over an hour. And this is what I infer from replacing the dry static conversion with moist static conversion in the Q matrix. And there's some resemblance to pick that up, or to pick this up. Some of it don't really mismatch to some extent. So you get a fair bit of it, not all of it by any means. And this gives you an avenue for saying, well, how well coupled your parameterization to large scale dynamics. Semi one to see large scale dynamics, you've got very coupling on this scale for your moist processes, which purely works out in a single column parameterization and the large scale dynamics. So this would be a jumping off point for trying to say, well, should this have been closer back or not? Well, we don't know the answer at this point, but that encourages some study, let's say. And then my final example, as there was a method which I really want to get in. So this is the one that really shows this is worth it. So I've already said that diagnostic calculated response spatially dependent forcing in topics, mainly for convection. So Jose was interested in studying the systematic biases in the tropical Pacific. So this is the reanalysis. This is a version of the climate model, and you see it failed to extend the high pressure circulation far enough west of the Pacific. This is a well-known systematic error in the unified model. And we'd already done a nudging experiment to suggest that, of course, this model would have the correct tropics. It's got a somewhat better answer, which suggests leaving something to do with the tropics. So this is associated precipitation error. So this is the actual analyzed precipitation, and this is the difference between the climate model analysis. Yellow bit is a very dry bit of the maritime continent. This is a wet bias about 20 degrees north, which is where the subtropical high should be. So this is not too surprising that the subtropical high hasn't extended over there, and the whole sort of convective region has been shifted a long way north. This is another diagram. This is the low level moisture conversion, which shows the same area as the one that's wet there, dry there. So that's the precipitation errors, and then they illustrate that error. So here's the precipitation error. So dry of the maritime continent near the equator, wet to the north of it. This is the wet bit shown before, and then this is the error in the convective heating increment. And show the same pattern, so that suggests that precipitation error nearly all convection error. Not too surprising with the topic, but expect mostly convection. And then you then show that there's also the same reverse motion error, which says that the, again, error with too much upward motion here, where you've got too much heating, too little vertical motion here, or downward motion here, where you have a large absence of heating. So this suggests that errors in vertical motion, errors in convective heating increment, and in final precipitation all very closely correlated. I guess you wouldn't be too surprised by any of that. And then finally, we do the transplant experiment. So here, so this is we use diagnostic to get both the vertical motion and divergent wind out of the 50-day forecast average over location, and after the analyses, and these are the errors in the vertical motion used by the diagnostic, as shown by the diagnostic. And then they show you this error in upward motion here over the wet region, error, reverse error, little vertical motion or downward motion where the precipitation is deficient. So it's the same pattern. Now, we then transplanted so in the diagnostic, we get put vector heating for the analysis and rerun everything with analyzed the vector heating instead of the liquid vector heating, and all the errors are wiped out. So, and that says that really, if you get convection in the right place, you've got the right answer. And so what you have to concentrate on is getting convection in the right place. And that's a very useful outcome. You've got wide convection in the wrong place. I won't go further into that. Examples involved in still being done better with. It would show that convection, very inadequate area where the surface wind was light. Typically happens a lot near the equator. In the equator, so there's a large area of light winds here, convection is insufficient, and that's wrong. If you look at the analysis, winds are light there, that's the right answer. The convection is a lot. And so the efficiency of the parameterization is that convection light wind. Parameterization experts are kind of decide what to do about it. It does show you can lead all the way through from an idealized model to down in the real system, and I think that will do. So reasonably accurate, actually useful. We've never used it proper, of course, and illustrate matching the unified models with both latent heat release and large subtopic stabilized. So to link the whole way across an idealized model to real system, and things you need to do to improve the real system. But that's obviously right there. Lots of debate already, but
Yeah, we had lots of debate. I don't know if there are any pressing questions now. Tobias?
Okay, I don't really understand how you use the G model to see that you have any error in a very naive way. What you're doing when you look at data.
yeah, so I take an analysis and a 3-day forecast. Run the diagnostic for both of them, and I see that and obviously the difference. There's an error in the forecast. I see an error in the difference in the diagnostic.
What is that or not?
So run the semi-geostrophic diagnostic to then work out what the vertical motion is implied by the SD approximation.
Yeah.
And I calculate that from the analysis and from the forecast. I compare them. There's a difference. So that means instead of just saying the model is got, if my model got there, I can see it appearing in a balanced diagnostic unified model. So I know that errors associated with the balanced solution, not just I know where it comes from. I won't convene anything. The unified model has all sorts of motions. I know it comes from the balanced physically unified model. So I can see why that related to convexity. But now that works. So I trace it back and now you say we need to do something about this error in the convection. So it all fits together. If I didn't have the diagnostic, I've got no idea why the vertical motion is wrong.
So maybe this is time to ask a question. So with my daughter the other day, it was quite a stupid red spot. And that's a very difficult question for me at least. But is it true that I mean the question I couldn't answer is why does this spot live? Why does it have such a long lifetime? Does it have to do with the fact that is the quasi-geostrophic approximation better on Jupiter?
Well, okay, that's well, the point saying about San Jupiter will be the vertical scale. So it's a shallow, something is shallow and quite likely to be San Jupiter. Aspect ratio is small. Now, the last talk I heard by Peter Reed said that starting to get some information from population about the vertical scale of deep.
Yeah.
And that's really the key to answer that question. Don't say any more because I don't really know exactly all the evidence you've got. The observation now starts to tell people things about the vertical scale on deep. And that will be very important using this aspect ratio.
Right.
So it may well be that they have a small enough aspect ratio instead of tropic dynamics, and therefore it's around.
Okay.
That's to expect that they actually know what these stuff are. John Messer has shown the vortex flows equation. The atmosphere is very shallow, and still is probably shallow.
Yes.
And ask the same question about what the field is.
Right. Okay. I hope I can
Well,
explain this to my daughter. She's just 7 years old, but
just tell her that it depends on what's happening in vertical.
yes.
And people starting to measure this from recent data
Right.
and don't.
No, I don't have a problem.
You ask people really.
Okay, thank you very much. I think we should stop there or can continue discussion over lunch. And